So let's go ahead and start. Hello, everyone. So we'll go ahead and jump right in today. We're doing a little bit more Psychtoolbox today. So let's talk a little bit about what the topics are left, because I kind of had to think about this and kind of figured out, I think, what we're doing the rest of the semester. So this is lecture 16. We missed one of our originally planned lectures. You know, there's supposed to be 20 in total, but we had one sort of free week already while I was away, and just generally I've gone a little bit, well, not as slowly as you might like, but a little bit more slowly through Matlab than I had sort of originally planned. So I think what we're going to do today is we're going to finish up, really pretty much finish up Psychtoolbox today. Which will be lecture 16. Now, I did have all this other stuff planned about we were going to do data analysis and stuff on plotting and all this stuff. I think I'm going to cut out quite a bit of it because it's really good stuff, but there's not really time to get into it in detail. And I don't think you'll need any of it really for the most part for the exam. I'll double check what I put on the exam again and make sure we cover anything you need. But I think actually at this point in time, you pretty much know everything you're going to need to know for the exam. And we'll talk about that a little bit more also. But so basically what we're going to do today is we're going to kind of go back to what we did last week, revisit that. We went really fast at the end, so we're certainly going to step back and kind of explain everything we've done so far on the McGurk demo, especially the stuff right at the end last week where we were kind of pushing to get done so that you'd have that code available. And that'll pretty much wrap up Psychtoolbox. I think what we'll try to do is next week just touch a little bit on stuff you can do with data analysis and play around with a little bit of data. The following week, just talk a little bit about doing things like plotting data with Matlab and using Matlab for that kind of thing. And then I think what we'll do is that last Tuesday of the semester, we'll use that as a catch-up day for your projects or your last problem set. So we'll have 2 hours, that are compulsory. You have to be here, for in class, but it's going to be all just you guys working on your code and me answering questions and stuff. So really only 2 more actual lectures after today. And these last 2, I probably won't ask you any problem set questions on problem set 10. Probably it'll just be building on what we do today. And problem set 10 will hopefully be not too bad. So I think that's the plan for now. Hopefully that'll give you sufficient time that last week to work on your final problem sets and your projects, and we can slow down a little bit for the last few classes of the semester. Okay, so just updating. So problem set 8 was due last night, a minute before midnight. I released problem set 9 as soon as I got it done, very early this morning, a couple hours after the other one was due. That's going to be due a week from Friday on the 12th of April. And that'll give you basically 9 business days to do it, or nearly 2 weeks. And then that means we can give you a full 2 weeks for problem set 10, which will be due on the 26th of April. And I think based on what I'm planning on putting in problem set 10, that should be plenty of time, so that hopefully you won't be spending all your time on that. You can spend some time on your projects and other classes. I know that you guys probably want your keys and your marks for the previous problem sets. Those will be released as soon as I can get to them. The keys will probably be more helpful than the marks because you probably know what you understood and what you didn't. So I'll release the keys first so that you'll have the information in them for your subsequent problem sets in case you need to adapt code or things like that. Or like to help you understand things you didn't understand when you submitted the problem set. So we'll do that, and what else was it? Oh, and not so much problem set 9. Problem set 9 will build a little bit on what we do in class. The one that was released last night will build a little bit on what we talk about today, but problem set 10 will probably build a little bit on what you did in previous problem sets. So I will make sure to get the keys out in the next few days so that those will be released in plenty of time for problem set 10. And I will try to mark as fast as I can once I get these last few lectures I have to prepare done with. Projects will then be due a few days after the last problem set in the study week on the 2nd of May. we'll talk maybe next week about like what you actually turn in. It'll mainly be your code, but you'll probably want to, turn in some written remarks about like how things went. I'm not too particular about the format, but we can talk about that next time probably. I would love for there to be a time to do like presentations of your projects, but I guess it'll depend on like how final they all are. So maybe we can do that like informally at a time we arrange, because really I want to show off my project as well. Although I have made about as much progress as you guys probably have, which is to say not very much. But hopefully that will all change pretty soon. Okay. So any other stuff? All right. And I just want to remind you guys, I know things have been busy recently with your your project presentations and the problem sets and so forth. I know problem set 8 was probably kind of hard, although most of what was in it you could have adapted from code that I gave you from class, right? So, and the idea of problem set 7 was to kind of teach you how to use the debugger to step through code and like figure things out if you don't understand them. But we are going to slow down a little bit now with problem set 9 and 10, hopefully, and with the remaining classes. And everyone should keep in mind, of course, that like everyone is doing, the class average so far is like way above what it really should be. So hopefully, if the last few problem sets are a little bit hard, that's not the worst thing. It'll kind of help correct the curve so that, I would love for you guys to all get like A++, but like that probably would raise some eyebrows that we graded too easily. So, the last couple of problem sets will be a little tricky, and you don't have to, if you don't totally understand them, that's, not the worst thing in the world, really, but, you should do your best. And keep in mind that, like I said, we've pretty much done all the content in class already that you'll need for the exam. The exam is mostly going to be more conceptual questions. You're not going to have to know specifics about coding, because really that's what the projects and problem sets are for. So the exam is going to test more of your general understanding of programming concepts, and that's actually something we'll talk about in the lecture part of today. Okay, so any questions or anything about any of that? Okay. So if you remember last time, we were doing this McGurk demo, which I know we rushed at the end especially. So we're going to go through that a little more slowly. Everybody should probably grab the code from last time. I will as well, and because we're going to be modifying that today. So I'm actually going to just make a lecture 16 code folder and copy the sounds and the latest demo file, as well as those PTB files that we're going to need. Copy them all in there. Okay, so we'll kind of go over what we did last time a bit more, and I think step through the logic of this whole program up to this point a bit, just so you guys get it. So you may want to open this up on your PCs, make sure it runs, and then, as I'm talking, you may want to use the debugger and step through some things. It's kind of up to you, because at this point, one nice thing is that, let's see, in this demo so far, we'll just run it right now. If I recall correctly, warning on the podcasts that loud noises are incoming. So if you remember, we did this demo where we said, now this is kind of a dumb example experiment, but we said, okay, what we want to do in theory is, see if we can induce something kind of like a McGurk effect by reading text. And obviously we saw the first time that if we just play a sound with text at the same time, that doesn't really affect how you perceive the sound in any noticeable way. And we said, okay, well, what if we blend two sounds together so it's a little ambiguous what the actual sound is? Then does the text that you display with the sound, does that affect your judgment of the sound? This is not really a real psychology question. I guess it could be if it turned out to be interesting. But it's mainly just to show off sound and what you can do with Matlab, where you can change stimuli in real time. But anyway, so what we're going to do here is see some words at the same time as some blended sounds.
Ga.
All right, so that sounded like a ga to me.
Ga.
That sounded like ga.
Ga.
That's another ga.
Ga.
Another ga.
ga,
I think that was a ba mostly.
da,
Da.
ga,
I think that was a ga.
da,
Da.
ga,
Ga.
da,
Da. And let's see how I did. All right, so remember what we did. This is just to remind you of what the paradigm is, right? So what we did is we actually, on each trial, we're taking two sounds, right? We have these sound waves of ga, ba, and da, and we're blending them together in some proportion. So I think the current proportion, if I open up the file, is 52% of one sound and 48% of another sound. So actually, I changed those numbers a bit. So that would be the current ratio, right? So let's see if I got those right. So when it's 52% ga, I said ga. When it's 52% da and 48% ga, it sounded like ga to me, apparently. Now notice that the text was da, so apparently that didn't bias me towards saying da. Ga and ba mixed together gave me a ga. Da and ga, I said ga. Ba and ga, I said ba. Da and ga, I said da. Ba and ga, I said ga. Apparently whenever you see ga and ba together, I tend to say ga. So maybe the ga masks the ba somehow. Ba and ga was ga. Da and ba was da. Da and ga was ga. Anyway. Oh, so that's interesting. Da and ga together in sound with the text of ga. I said ga. Who knows if the text influenced my perception, but maybe. Da and ba together, I said da correctly. Okay, so whatever, that's the task. It's probably not a very good psychology experiment task yet. There are a lot of things that would be better to do, and if we had a million years for problem sets, I would probably ask you to do one of them. Because really the best thing to do would probably be to blend the sounds together in different proportions until we found the exact proportion of blending each pair of sounds together that made it perfect chance as to whether people got it right. So maybe when you blend ga and ba together, there's a tendency to hear ga more than ba if they're almost equally blended. But maybe if you make it 60% ba, then it's exactly ambiguous as to whether it's ga or ba, right? So it might kind of depend on the sounds and the proportions. And so what it might make sense, what might make a better actual experiment would be to say, all right, we're first going to use only sound and figure out in the different combinations of each pair of sounds, what are the mixing percentages that make it perfectly ambiguous which sound you're hearing, and then see if text influences that, right? But we're not going to do that because that's going to take too much time. But it might make sense to think about topics like how you might do a psychophysics experiment like that, say, for example, on the exam. I might ask you some questions about, experiment designs and how they might go. So just be thinking about things like that. Okay, so anyway, so that's the experiment. Everybody got that? Anybody have issues running the code just as you should be able to run what we had from last week. Anybody have problems with just technical problems running this on Matlab? You guys are welcome to run it now if you want to make a chorus of gas and bas and everything. Or if you've got it turned down so it's not actually making noise. That's okay. All right, everybody on board with it, just the code just working? Okay, so let's actually, maybe it'll help to do it this way. Let's step through using the debugger like we did in problem set 7. And let's just go sort of bit by bit through this code and remind ourselves what it does before we make any more modifications. So, and again, sorry that this projector here is kind of blurry. That one's a bit clearer, but of course, right now, we should all be in sync with our code if you've downloaded the stuff on the Google Drive. So, in theory, you should just be able to look at your own screen if things are unclear. Okay, so let's try running the McGurk demo 2 again, but this time go through line by line. Okay, so first thing we do is define the cell matrix that we call syllables, right? And remember what we said about a cell matrix is it's a special kind of matrix that contains other matrices, right? So after line 3, we have this 1x3 cell matrix, each of which has each item in the cell being a string, right? So we can do that. Define just a simple numerical double variable as number 10. Make another cell called instructions text. You may notice that for in this case, like this is also it's a 3 by 1 cell. The only difference meaning syllables is a 1 by 3, right? Meaning it's a row of information, right? The three things are laid out in a row. Instructions text, because it's a little bit easier to write it this way, is a 3 by 1, meaning it's a column, right? There's 3 rows by 1 column of data in the instructions text cell. And so each item in this matrix is one of these strings, please place the index, blah, blah, blah. The only thing to note is that if it's too long to display in this little pop-up box, it says, like 1 by 125 char. Oh, that was weird. What did I do? Somehow I magically... Oh, I bet I know what I did. I bet I did something with the presenter tool. All right, so I'm going to have to quit that. Do that again. Okay, so you get this little pop-up, right? That's so weird. Every time I hit the laser pointer, the task goes on. I have no idea why that is. All right. In theory, the laser pointer should only be a laser pointer, but I guess it's not. All right. So I won't be hitting the laser pointer again. I'll just use the mouse to point. Okay, so what you see is when you mouse over instructions text, it lists 3 things. That thing where it says 1 by 125 char, 1 by 145 char, that's simply saying I've got a string in that position, but it's too long to display as itself, literally. So it just tells you that it's a string with 125 characters and then a string with 145 characters, right? So if I want to look at what instructions text is on the command line, it tells me the same thing. But then if I wanted to specifically see exactly what that first item is in the cell matrix, that's instructions text, curly brace, 1, end curly brace. It says, oh, okay, that's equal to the string that I put in, right? So that little 1 by 125 char is just it's a way of abbreviating the full string because there's not enough room on the screen to display the full string. But it's telling me that these 3 strings of orientar, these 3 strings right here, right, that I put in the cell matrix, that's what it has in it now. Okay? All right, so let's move on. So now we're going to define another cell matrix. So we're using a lot of cell matrices. If you don't understand these, they're a little weird to get around, but again, remember, they're just a matrix that contains other matrices of any type, right? And so they're useful when you've got different things of like possibly different lengths. So this is going to be the text labels on the screen that tell us what key to respond with, right? So each one of these is a syllable followed by \n, which means next line or new line, and then parentheses 1, parentheses 2, parentheses 3. So those are the 3 labels that appear on the screen, right, that say for ba, press 1, for da, press 2, for ga, press 3. So those are just the 3 things that we'll want to print on the screen. The spacing, this is just a variable we're going to define how far apart those labels get printed. So that's just assigning a name to a number for convenience. Response keys, again, another cell matrix. Remember that we said when we get a keyboard response, we can get a key code. And one weird thing about Psychtoolbox is that it doesn't just call the 1 keys 1, 2, and 3. It calls them 1 exclamation point, 2 @ symbol, and 3 pound sign or octothorpe, because it actually represents the codes for the number keys that are above Q, W, and E differently than the ones that are on the numerical keypad, right? So we have to, I think I showed you last time how you can learn that, right? So if you want to get the key code for something, you can say my key code equals KB wait. That's the Psychtoolbox command that waits for a key press, right? So it waits for a key to be pressed. I'm going to hit the 7 key now above the keyboard. All right, so I typed a 7. So if you look at what my key code is, oh wait, you know what? I totally lied to you. The first thing it gives you actually is when the key was pressed. So that's not going to help me. What we should do is say like the key time and then the key code. I'll call it my key code again to be consistent. And remember that we said last time you can put in some extra parameters for KB wait. Basically, this is telling it that it's waiting for a key press from any keyboard device. You see it works either way, but this is a slightly better way to do it. So if you ever use KB wait, you might want to use KB wait with the empty brackets and a 2, which just basically refer to the mode of what you're waiting for. So it works about the same whether you do it this way or with just the empty parentheses, but this is slightly better, so I suggest using it this way. But the details of why you might do that are not too important. Okay, so if we do this, so now I'll hit the 7 key again. And now we have my key secs. So that's the time I hit the key in whatever units. I mean, it's a lot of units. It's probably, again, I think the units are seconds since you turned on your computer, but it doesn't really matter. More importantly, we get a key code out of it, which remember we said is a matrix of 256 yes or no values, logical values, right? True or false, represented by 1 or 0. In theory, since I only hit one key, only one of them is true, which is that one right there. And of course, that doesn't help me very much because I don't know, like, you know, it has codes for 256 keys, which is more keys than I actually have on my keyboard. But I don't know what key number 34, 35, what key 36 is in whatever internal representation Psychtoolbox has for key codes. So what I really want to do is say KB name, which is the function that translates this key code into some sort of human readable name of my key code. And that tells me that what I hit was the 7 key or the 7 ampersand symbol key, right? So again, it's a little complicated because if you use PsychoPy, remember that it just kind of gives you the key that was hit directly as a string. Psychtoolbox has a couple of steps where you have to first get the key code and then translate that into the name of a key. But it's not that big of a deal to figure out. So, I mean, again, you can kind of play along here if you want and, you know, find the key codes of some of the keys on your keyboard. Most of them, if I do this again, most of them, let's say if I press the J key, are just going to be like the key code name of, or the KB name, or the, you know, the name of the J key is just J. But, you know, if you hit something, oops, if you hit something like the delete key, for example, like what's the name of that going to be? Apparently it's delete in all caps, right? So if you had some task where it was critically important that people press the delete key, you'd have to kind of do, you know, punch these couple of lines of code into the Matlab command line, and that would help you figure out that the name of the delete key is the word delete in all capitals, right? So you can do some others. I can hit tab. I mean, it's going to be tab in all caps. Oh, no, tab in all lowercase. Who knew? Good to know. Let's say I want to hit the little curly Q symbol on the Mac that we call command. Let's see what that is. Oh, it calls it left GUI. Who knows? That's probably what you also get if you press the Windows key on a Windows keyboard, if you guys want to try that. I don't know if you do. Anybody want to try getting a key code for the Windows key? Anybody got it? I'll get some others while you're trying that. Let's see. Let's see what so the Mac, on the Mac, the Option key or Alt key is the same key. Let's see what that one's called. Oh, right Alt. So it refers to Option on the Mac as Alt. Anybody got the name of the Windows key so far? Okay, so it's left GUI. So basically, Psychtoolbox treats the Windows key and the Mac command key as the same. Possibly worth knowing. My general recommendation to you, ooh, caps lock. Let's see what caps lock comes up as. Comes up as caps lock. All right, so my general recommendation to you is, of course, because, you know, it's a bit weird to use these keys like Alt and, you know, things like that. I would recommend sticking to the letters of the alphabet and the numeric keys for the most part, just because they're easier. But at any rate, if you need to figure out the name that Psychtoolbox uses for the different keyboard keys, that's the way to do it. So Anyway, what we said back here in the text in the script was there are 3 response keys we might use. One of which has the code 1 exclamation point, one of which has the code 2 @ symbol, and one of which is the 3 ampersand. And if you forgot and just called those 1, 2, and 3, it would only work with, the ones on the. Put this in the podcast. Oh no, I can't. It's too short. The ones on the numeric keypad over here. These are the ones that have the labels 1, 2, and 3 by themselves. But the ones above the Q, W, E keys are the ones that have these names here. Okay, so enough about response keys. Let's keep going. And again, I recommend you guys kind of step through and play around with this yourself as I'm talking. So text color, I only defined very briefly, but this is just a red, green, blue color code for what color I want my text to be. This is this sort of general code that is used for all colors. So if I start up like Photoshop and go to the color picker, for example, let's see if you guys can guess what color. All right, what color is 255, 255, 255? Right? Everybody together. White, right, excellent, good job. All right, I wasn't sure, I don't know if people are used to doing this in Photoshop or not, or you know what I mean, if you're used to this coding system. It's the same, similar coding system to what's used in PsychtoPy, but with a different range of values, right? Because in PsychtoPy, colors are defined between -1 and 1, right? Like the red, green, and blue are defined by -1 to 1 ranges. In Matlab, it uses the convention that general programming more often uses, which is that they range from 0 to 255. So, if I want a color that's all green and no red or blue, like this one, I put in 0 red, 255 green, 0 blue, right? And this is actually on problem, not for colors, but just in general for pictures. This is in problem set 8 that I just posted. The reason for this is really because color values on your monitor are represented by 1 computer byte of memory for the redness, 1 computer byte of memory storing the greenness of the color, and 1 computer byte of memory storing the blueness, and 1 byte of memory can only hold 256 values, or in other words, the values between 0 and 255. Okay, so that's why we have 255, 255, 255 to represent the color white, okay? But if we wanted the text to be red, for example, the color codes go red, green, blue, so red would be 255, 0, 0, or you can make up some random color, whatever you wanted, as long as the 3 numbers in this stay between 0 and 255. Okay, so that's the text color. And then we said the sound proportion is just a number we define. This is how we're going to blend together the 2 sounds that we kind of blend to create this ambiguous sound stimulus that's part 1 syllable and part another. If we say it's 0.52, what we're saying is really when we pick 2 syllables, the one that is represented a little bit more will be like 52% of that signal will be in the blended sound, and then the one that's represented a little bit less, that'll have 48% of itself in the blended sound, okay? So that we'll see how that works in just a minute. Okay, so then we put in this line. Like I said before, you don't have to know how this line works at all. This is just our magic wand to basically automatically clear away all the Psychtoolbox stuff if our code crashes. And it's a bit nicer than having to do that thing where you have to hit Control-C and everything, which I actually wrote into problem set 7 because until a couple, like I said, a week or 2 ago, I didn't know this trick, and then my friend sent it to me. So now this is much easier than like having to force quit Matlab when your code crashes, which is kind of nice. So we just include this line to magically clean up Psychtoolbox in case we crash. And now we're basically onto the main code, right? So let's step through the next line. This is just a convenient thing to kind of count how many syllables we're going to be working with, right? So we use the length function in Matlab to see what the length of our syllables matrix is, right? So since syllables is a 1x3 row matrix, the length of it is 3 items, right? And the nice thing about length is it works equally well for row matrices like this one and column matrices, right? So if I want to get the length of syllables, it's 3. If I want to get the length of, oops, get rid of Photoshop there. The length of instructions text, that's also 3, even though the size of syllables is 1 by 3, and the size of instructions text is 3 by 1, right? So syllables has its 3 strings in a row, instructions text has its 3 strings in a column, but length doesn't care. Length just says what's the length of it in whatever direction it is, right? And again, length has some weird behavior if you have things that are not just a pure row or a pure column, so don't worry about that. But it's a useful function for just kind of, if you have a row of things or a column of things, finding out how many there are, right? So then we can just toss that length into a variable called in syllables, which you might imagine is a helpful thing to just keep in mind. And again, that lets us make our code pretty extensible, right? Because maybe we wanted to add another syllable like va or something like that. You know, then we just have to add it on this line. We'd have to make a sound file for it, obviously. We'd have to add a response key for it here and here. But other than that, our code is pretty much extendable automatically to any number of syllables. So it's sort of nice to do that in the code rather than, or figure that out in the code rather than, you know, sort of assuming it's always going to be 3, right? Because who knows, we may want to extend our experiment to 4 or 5 or 6 syllables. Okay, so now we're going to do a couple things here. We're going to read in all of our sound data, okay? So I'm going to go through the next couple lines. This is just creating some empty matrices. Remember, this is just like what we did in Python, where you would create an empty list and then add things onto it. So we're going to do the same thing in Matlab, right, where we create an empty cell matrix, which is going to be called sound cells, and an empty regular matrix, a numeric matrix, with these square brackets, right? And then we're going to sort of add on to the end of them. And by the way, Matlab is going to complain about this a little bit, because Matlab is, well, not that one. Matlab's a little bit ornery about that kind of thing. Well, let's see. It gives me a little squiggle here, basically saying what you can see is what the squiggle represents is, if I go over here, come on, Matlab. There we go. What the squiggle represents is, not that one, here. This is basically saying that what I'm trying to do there on line 24 is not as speedy as it could be. This is not something we need to really worry about in this code, though, because we're not super concerned about the speed of this. But Matlab does give you helpful messages. Basically what it's saying here is, well, you can do this. You can create an empty matrix and then add an item to it, then add an item to it, and then add another item to it. But it would really be faster, computationally speaking, to create a matrix with 3 items in it all at once. And there's reasons for that. They don't matter. Just kind of worth knowing. So you can kind of ignore these little warnings about that kind of thing. Okay, but what we're going to be doing is disregarding Matlab's warnings about how slow our code is going to be, and we're going to create some empty matrices and then add some items into them one at a time. Okay, so we're going to have a for loop from where I, which is going to be our counter variable, goes between 1 and n syllables. We know that we have 3 syllables, so it'll go from 1 to 3. And the first thing we're going to do is use each syllable to construct a file name, right? So we're going to take the list of syllables that we defined, ba, da, and ga, take the ith element of it, meaning, you know, the first element this time, the second element the next time, and so forth, and then tack on a dot wave to the end, right? So if we do that, we've got ba dot wave, right? And the reason we got that is because, let's maybe break that down a little bit, because that's probably one of those lines that's a little confusing if you're not used to Matlab yet. Let's go just do this on the command line. We've just executed this line of code, so we're not going to change anything if we execute it again, right? So if we want to break down what's happening here, right, what we get eventually is ba.wave. What we did is we took syllable, well, if you look at what syllables is, right, it's this cell matrix of 3 items. I is the number 1 right now, right, because it's our counter for the for loop and it starts at 1. And syllables, that's a curly brace, I, pulls out the ith, or the first element from the cell matrix, right? So that gives us just the string ba. And what we're really doing is when we put, for example, ba and dot wave into these square brackets like this, that's a way of saying, like, we're making a new matrix that is joining these two matrices horizontally, right? So if you do that, you just get ba dot wave. So if you break down this whole line again, what we're doing is we're taking the ith element of syllables, which is ba, joining that using these square brackets with the dot wave string. That creates the string ba dot wave, and then we assign it to a variable called file name, right? Okay, so that lets us say, I mean, that makes an assumption, right? Basically, the code is making an assumption here that whatever we've defined as our syllables, ba, dot, and ga, have the same file name as the syllable, right? Which is, I think, a reasonable assumption to make since we both wrote the code and named the files. But, you know, if you didn't want to do that, you could have separate file names kind of hard-coded in, maybe in this top section. Okay, so now we know the name of the file we want to read. It's ba.wave. Now we use this wave read function of Matlab, and what we give it is our file name, right? And what it's going to give us is three variables called sound data, sampling rate, and in bits, okay? And remember, this is how we call a function that has multiple output values, right? So wave read has three outputs, one of which is the actual sound data, the sound wave, one of which is the sampling rate, meaning, remember we said, like, you know, I don't know if you guys are super familiar with audio stuff, although you will be after problem set 9, because there's a lot of sound stuff in there. But, you know, if you have a CD, every second of that CD's audio has 44,000 samples in it, right? Another samples meaning, like, you know, little tiny recordings of chunks of the sound wave, right? Now, of course, you don't always have to record at the same sampling rate because, you know, if you're Skyping with someone or downloading a podcast or something like that, you don't always care about that much quality, right? You might want to get something that's sampled a little less frequently because then the file size is going to be smaller. So, you know, you might get something that's sampled at 22,000 times a second or 10,000 times a second or something like that. Okay, so anyway, that's all information that's in this wave file. So the Matlab Wavery function is going to look in the file. It's going to not only get the actual data out of the file, but get us what we would call like metadata, like stuff about the data telling us like the complexity of it. So that's the sampling rate and the number of bits. And the number of bits is a different representation of quality, basically. Well, it's not that important. All right, because we don't actually end up using it in the script at all, but it is something we can get out of Wavery. Okay, so when we get that, what we get is sound data is a numeric matrix or a column matrix, right? Because it's 9,537 by 1 items. They're double, so that, you know, it's a numeric matrix. So that's our actual sound wave. We get the sampling rate. Oh, in this case, it's 22,050 apparently, so half CD quality. And number of bits is 16, but we don't really care about that output variable, so we won't use that again. And just to forecast, I think I did this last time, if you want to look at that sound wave, Matlab's got a nice function called plot. And if I can just say plot sound data as we're running, and it gives me a nice little, this is like doing a line graph or something, right? So it's just giving us a line graph of the 9,000 and whatever numbers in our sound wave, right? So a sound wave, right, is just a bunch of numbers. And when we graph those numbers, it looks like, well, a sound wave. It's hard to, sorry, it's like hard to, if you're not used to thinking of stuff in this way, this is maybe hard to think about. I know we looked at some of this stuff last year in C82 but all reports point to the fact that class was hard too. So, so you may not have gotten it the first time around either. But basically, right, like what this is saying is essentially, you know, when your voice vibrates the air, right, what your voice is doing is kind of pushing air in this pattern where it's like compressing and extending it, right? And basically, what a sound wave really is a line graph of air pressure over time, right? So when my vocal cords vibrate like this, Well, that's a bad example. But what it's doing really is it's like pushing, when when your vocal cords vibrate, you're kind of pushing, compressing and uncompressing the air rapidly so that you have rapidly alternating patterns of high and low air pressure. And that's really what's being graphed in a sound wave, right? It's like high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. And, then this causes our ears to vibrate similar ways, and, magic happens in the brain and you hear it as sound, right? But anyway, so all that data goes into the computer, right? And it's just recorded as numbers that you can then graph and see visually, or you can use these numbers to feed into a speaker and vibrate the speaker the same way, in the same pattern of vibration that vocal cords originally vibrated, or that your ear will vibrate to hear the sound, and it'll produce a sound, right? But we can see our data, and you can see, if you look down here, this is the number of data points, right? So you can see that there's about 9,500 and whatever data points in this sound wave. Okay, that kind of makes sense to people, how this sound wave is represented. Okay, that's good because you have more picture and sound stuff, like the stuff about how pictures and sound are represented in problem set 9. Okay, so let's keep going. What we're doing in this next line is we're just putting that sound data into a cell matrix that we called sound cells. And I pulled one other little trick here that I think I briefly went over last time, which is I used this little apostrophe guy here. This apostrophe guy basically flips a matrix, or transposes a matrix, if you remember your matrix linear algebra stuff. This is only because, for some dumb reason, Matlab likes to give you the sound data as a column, but Psychtoolbox likes you to give it sound data that is a row. Okay? So all the transpose thing does is say, here's sound data, right? It's a big column of numbers. Here's sound data with an apostrophe, transposed. That's a big row of numbers, right? So if I do it with some other, like let's just call this my random data, is a random matrix that is 2 by 5. So that gives us a 2-row by 5-column matrix of random numbers, right? If I want to see what my random data is transposed, I just put the apostrophe on the end. And it's the same numbers, but with rows and columns flipped, right? So here, 4387 and 3816 were the first column. Now they're the first row. Here, 7655 and 7952 were the second column. Now they're the second row, right? And so on. So all that's doing is it's flipping sound data from a column into a row, and then putting that row into this sound cells cell matrix, right? So now sound cells is a cell matrix with one numeric matrix inside of it, which is a 1 by 9,537 matrix with that sound wave in it. Okay, and the next thing we're going to do is, remember we said all of our sounds are not the same length. They're close to the same duration, but not exactly the same duration. So if we want to line them up so that we can average them together when we're blending them, we need to know how long each one is so that we can kind of adjust the lengths to be the same. So we're going to want to record our sound lengths. So our sound data is 9537 by 1. Thus, we would expect the length of that sound data to be 9,537, right? So we're just going to put that hopefully into our sound lengths matrix, which it is. And remember what we said is this was in the previous problem set, I think, number 7. What this magic word end does is refer to the last item in the list, or the last item in the matrix. And if you say end plus 1, basically it lets you put something into the position beyond the last item in the matrix, which basically is like in PsychoPy saying like, my list dot add, right? You guys remember that? So if you, it's a bit funny, right? Because basically, let's just look at this quickly. Let's do this on some example data. So like, let's make a variable called sum cell, for example. And we're going to set that equal to be an empty cell matrix. So it tells us it's an empty cell matrix. If we get the size of sum cell It's 0 by 0, meaning it has like absolutely nothing in it, right? Now, if we say, we can do some things like if we say some cell end, that's going to give us an error, because actually, if something has nothing in it, we can't refer to the last item in it. This is a little funky, though. What we can do is say, well, we also can't just look at what's in n plus 1, because also we don't have that many items in the matrix. But if we want to say some cell n plus 1 equals first thing or whatever that's going into the cell matrix, that's okay. All right. So in other words, this n, if we use n plus 1 and say that equals something, that's saying, oh no, I don't want to get the item. I don't want to get an item that's beyond the end of this matrix. I want to add an item one beyond the end of this matrix. And of course, if you have an empty matrix, one item beyond the end of it is just the first item, right? Because it was empty. So if we extend an empty thing by 1, we just have a thing, matrix with one thing in it. Okay, so this makes a little more sense, I think, what we've got once we've got one item in here. I know it's a little bit funky in the case where it's got 0 items in it. Because now some cell is a 1 by 1 matrix, right? Meaning it's got one item in it. And that item is the string first thing. Now, if we want to look at what's the last thing in the cell matrix, we can use some cell end. And you see that looks a little bit different than here. This is a funky kind of display thing. But basically, this is how Matlab tells us this is a cell with a string in it, because it puts the quotes there. This is just the string itself, right? So if we want to get the end element out of some cell, which in this case is the only element in some cell, we can say some cell end. Now what we can't do is we still can't say some cell n plus 1 by itself, because that's basically saying, like, give me the item that's one beyond the end of the list, right? And obviously there is no item beyond the end of the list, because it's the item, because the list ends at the end item, right? But if we want to say some cell n plus 1 equals number 2 or whatever, that's okay, right? Because we're saying, yeah, we know there's nothing beyond the end of the list now, but make the thing that's one beyond the end of the list the string number 2, right? Is this kind of starting to make sense to people? So now if I say some cell end, I get this, whatever the last item is, okay? All right. And just to remind you, because hopefully you should have gotten this in problem set 7, but I haven't looked to see how people did on this yet. If I go back to my little random data matrix, right? So here's that 2 by 5 matrix of random numbers. If I want to use end in other contexts, I can. So like I could say my random data. Now if I wanted to get like the second row, third item, I would do something like this. My random data, round parentheses, 2 comma 3, which is going to give me the second row, third item, which should give me 0.4898, right? But let's say I wanted to get the second row, last item, regardless of the size of this matrix. I could do something like my random data 2 comma end, and that gives me the last item of the second row, right? And I could flip this around. I could say, give me, the third column of the last row, however many rows there are. That's going to give me the 4898 again, right? So you could put end in either or both positions. If I want to get the very last item in both dimensions, that's my random data end, right, which is the last item of the last row. And you could even do some things like, this was also a question on the problem set. If I wanted to get all items in the, let's see, all items in the last column, I could use that colon operator, right? Which gives me all items in the end row, right? Which is equivalent to saying, like, colon comma 5, right? Because the 5th column is the last column. But if I do it this way, I don't have to specifically know ahead of time that there are 5 columns. Okay, so hopefully that's a little bit more on how end works. But in this context, all we're doing is using it to add one item to a cell matrix or a regular matrix, right? So now let's get through Today I think is mostly going to be stepping through this code. That's okay. We can even push some stuff back till next week. But let's get through to line 37 and then take a little quick break. I think we can go a bit faster then because you guys have seen some Psychtoolbox stuff before. So let's step through the rest of this for loop. Remember, we're not done with the for loop yet, so we go back to the beginning. Now I is 2 instead of 1 because I is going to go from 1 to 3. We're going to make our second file name, which is now da.wave, right? Because the second item in the syllables list is da. We're going to read in that sound wave, which is now going to be a 9453 by 1 double. Still the same sampling rate and number of bits because the sound files were made the same way, so that makes sense. Now we're going to add that sound data onto the end of sound cells. So now you see that sound cells is a 1 by 2 cell, right? So the is extended so that one item beyond the end is now this new sound data that we read in, right? So now we've got 2 matrices inside the sound cells cell matrix. One is that 1 by 9537 matrix representing ba, and now one is the 1 by 9453 matrix representing da. And this line, we're going to add the length of da, or of the da sound wave, onto the sound lengths matrix. So now we have a 1 by 2 matrix with those 2 lengths in it. And then we're just going to do that same thing again for ga, which should give us 3 sound waves in the cell matrix, 3 lengths. Apparently ga is the longest at 9,675 samples. And then we've gotten to the end of the for loop, right? Because I went from 1 to 3. I got to 3, so we ended the for loop. And now we go on to line 29. Okay, so real quickly, let's go, well, not real quickly, but somewhat briskly, let's go through this little loop also. Which, remember, like we said, what we're going to really want to do is, we've got 3 sound waves of different lengths, right? But what we're going to be trying to do is averaging these sound waves together, but you can't do that if you can't average together 2 lists of numbers if the lists are of different lengths, right? So what we're really going to do is take the shorter ones and add some silence to the beginning of them so that everything adds up, right? So that's what we're going to try to do. Now again, this is maybe not the best way to actually align these things. The best way would probably be to find like corresponding points on the sound waves and kind of trim them up so that everything matched up as well as possible. But this is fine for now, okay? So what we need to do to know this, first of all, is find out what the longest sound is in our list, right? So we have the sound lengths matrix. We know that ga is the longest one ourselves, but we have to tell Matlab that. So we use this max function, which just finds the largest value in a matrix. So we know the max sound length is 9,675. So what our algorithm was going to want to do is make all of the sound wave matrices that long, right? By adding some zeros to the beginning of anything shorter so that it becomes 9,675 samples long. So what we're going to do is we're going to have a for loop going through the 3 syllables again. So I is now 1. So now we're going to check to see if the current, the length of the first sound file, if that length is not equal to the maximum length, right? Because if it is equal to the maximum length, like if we're currently on the longest sound wave, we don't need to do anything to it, right? So we're only going to do this stuff inside the if statement if we are on one of the 2 shorter sound waves. So if the current sound length parentheses I, right, the first sound length, is not equal to the maximum sound length, which it looks like they're not, right, because the first sound length is 9537. We go into the code in the if statement. So now we're going to compute the difference between the maximum sound length and the length of the current sound, right? So 9537 subtracted from 9675. Who's good at math? That should be 138. Is that right? Oh, score. All right, cool. So if I could do that a billion times faster, I would be Matlab. Okay, so we know that we need to add 138. If we want these 2 sound waves to be the same length, we need to add 138 slots or numbers or, samples of silence to the beginning. So what we're going to do is say, all right, whatever's in sound cells I right now, we're going to replace it. And we're going to replace it with a matrix formed by what's currently in sound cells I, right, which refers to the first sound wave. And then we're going to also put in a matrix of zeros that is 1 by whatever the difference is. So let's break this down slightly. The function zeros is just a simple little function that gives us like however many zeros we want. So if we want a 3 by 8 matrix of zeros, hey, look at that, all the zeros a man could ever want. So we can do that, right? So if we want, in other words, if we're saying we want to add 138 zeros, which represent silence in a sound wave, we just can say zeros, and remember that we have our sound waves laid out as columns, right? So we want 1 by 138 zeros, right? So that would give us 138 zeros. If we did want a row of zeros, we could do, 138 by 1, right? That would give us a tall row of zeros, but we want 1 by 138. And basically what we want to do is we want to join that together with our sound wave, right? So let's let's plot our current. So let's call this old sound wave equals, so what's it? Sound cells has our 3 sound waves in it, right? So the one that we're working on right now is the first one, right? So if we want to look at our old sound wave, that's what we had, right? I keep trying to do, I have this extension that lets me do the Windows thing where you drag the window to the top of the screen and it resizes it, but it's not on this account. Okay, so that's our old sound wave that we plotted just a minute ago. You don't have to know what I'm doing here, but basically I'm going to just do this to kind of save what's in that graph. And now let's run this line of code. Okay, so now let's see what we've got. So let's say new sound wave. Oops. And that's now equal to what's in sound cells 1, because we just replaced what was in sound cells 1. And let's plot new sound wave on top of the other one in red. Okay, so it's a little hard to see. It feels a little bit like you're looking at a 3D movie out of focus. But if you zoom in, I think I can do this with the projector. What you see is the blue line, which was the old sound wave, kind of has a little bit of silence at the beginning and then like goes into waving up and down. The red line now has a bit more silence in the beginning and then goes to bumping up and down. Everybody see that? So what we've done is we've added in 138 zeros to the beginning of the sound wave so that now it's 138 samples longer, okay? And again, we did that we made the zeros function to create the zeros. We got what was formerly in that cell with sound cells, curly brackets I, and then we joined those two together like this by putting them side by side within square brackets. All right, and then we assigned that back to the ith element of sound cells, or the current cell. All right, everybody kind of cool with that? All right, so now, hopefully if that makes sense, we're just going to do the same thing with the second syllable, right? So we're on syllable number 2. The sound length of the second syllable is also shorter than the maximum, so we're going to do the same thing. And now you'll see that sound cells, the first 2 items in sound cells, now have the same length as the third one, right, which was the longest one. So now we've added zeros to both of the first 2 sounds in the beginning, or silence to the beginning, to make them equal in length to the third one. And now when I is equal to 3, when we run the for loop one more time, the if statement this time is going to be false, right, because this sound length is equal to the maximum sound length, so we don't have anything to do with that one, and we're done, right? So what we've got so far is we've read in all of our sounds, and we have put them in a cell matrix, and we have equalized all their lengths by padding them with zeros in the beginning, so that then if we want to average them together, we can do that, because we have the same number of items in each sound wave. All right, any questions so far? Okay, so welcome back. So I think what we're going to do, if it doesn't screw things up too much, is I'm going to actually just remember where we are. We're at the initialized psych sound. We're going to, you don't have to exit your debug mode. Actually, I should have said that first. But I'm going to exit mine so that my presenter tool does not screw up the Matlab. So I want to do just a few slides of like theory stuff. I was going to do that after we kind of finish stepping through this, but for time I want to make sure we get to these first because I think it's worth mentioning this stuff. And it's just quick conceptual stuff, but I figured I'd throw this in. So this is something I should have actually probably covered in this class a long time ago. I was trying to keep out too much like computer science theory from this and focus on the practical stuff, but I think this may help you, this terminology may help you with your exams and problem sets and things like that. So this is a concept that was advocated or described by a computer vision guy named David Marr, a very smart guy who didn't live very long, unfortunately. He died of leukemia in 1980 after only, 35 years alive. So, didn't have much time for a career, but he made a splash while he was alive. So he was you could call him a neuroscientist, a psychologist, or a computer scientist. He studied vision. His main thing was like models for how our vision works, like computational models trying to model how the biological systems of our visual systems work. So his specialty was computer vision, but the thing that is relevant to us is in his book on vision, which was actually published after his death in about, I think, 1982, he described something that he called his 3 levels of analysis, or that people now call Marr's 3 levels of analysis for information processing systems. And he was talking about this with regard to describing vision, but it really works for any type of computation. So although it's in a vision book, it's a good general concept for programming. And I think it's good to think about problems on these 3 levels. And this is something you get taught as like a first-year computer scientist, I think, in most programming curricula. We haven't talked about it, although I've been sort of implicitly using these terms. So I just thought I'd like spell these out a bit more so that we could use them in the future. So Marr basically said that problems can be described on 3 different levels depending on how specific you want to get about the problem. And the least specific of these is what he called the computational level, meaning like what do we want to compute and why would we want to compute it? So this is you can sort of think about the computational level as being mostly what I ask you to do if I give you a problem on a problem set that's pretty vague, right? Like write me a program that finds prime numbers, or like write me a program that implements a psychology task, right? So we want just a kind of a verbal description of what the problem to be solved is and why we want to solve it, what information we have to work with, and what information we want to end up with, right? So if I tell you, I want you to generate me a program that generates prime numbers, I'll need to tell you some things like, well, the information you have to start with is basically number theory, and what I want you to produce is a certain number of prime numbers, or all the prime numbers below a certain amount, or something like that, right? But the computational level is not concerned with how you solve the problem. It's just the level of analysis where you think about what the problem is to be solved, right? So this is the least specific level. In computer science, you don't really have to worry about this one as much because usually the computational level is the obvious one, right? We know what problems, generally speaking, we want to solve and how we solve them, although it is good to sort of specify these details, right? So like, as you'll see in problem set 9, I started some functions for you, and it's good practice to sort of put in the beginning of a function like what comes into it and what is expected to go out of it. And that's sort of, it sort of touches on the other levels, but that's kind of a computational level sort of thing. Like, what information do you have to put in and what information do you want to get out? Okay, now the next level, and this is the word we've been throwing around all year, and the level I really want you guys to understand things on most is the algorithmic level. And basically the idea of the algorithmic level is in what sort of ways can you represent the data, and what are the steps in the algorithm that solves the problem? So I've been asking you a lot of problems like this, I think especially in like problem set 7, was it 7 I think, and some in 6 as well. I asked you a lot about algorithms saying, in some cases I would say, don't refer to anything specific about Matlab code or Psychtoolbox code or CyclePy code or Python code. Just tell me about the algorithm, an algorithm that could be implemented on a computer, it could be implemented on pencil and paper, etc. Right? So the algorithm is, like we said before, the pure logical steps that you have to undertake to solve the problem, given certain, data structures and concepts like, okay, well, we have a list of numbers. We don't really care about how that list of numbers is represented in a computer or on paper or whatever, but if we have a list of numbers, then what can we do to that list to produce the output we want to produce, right? And that's what I've been trying to, sort of enforce to you guys doing in the problem sets is when I ask you, like, how something works or, what the steps are in solving a problem, is I really, and this is why I should have gone over this earlier, what I'm really looking for is an answer that answers it at the algorithmic level without referring to a specific variable or, just like translating lines of code from code to math. I really want you guys to sort of take that extra step and isolate the steps in the process from the specific code, right? So going further down is the implementation level. So this is what you're doing when you actually have to write code, right? So once you've planned out your algorithm, you have to actually put the algorithm into some kind of physical system, right? Now again, the thing about the implementation level is this could be in lots of different things could be used to implement an algorithm. You could use a computer, which obviously will have to be programmed with code. You could use a pencil and paper. You could use neurons and so forth, right? So all kinds of things could do the implementation. And of course, to some extent, these levels all interact, right? So, if I want to display a psychology task or blend two sounds together or something like that, I pretty much have to do that with a computer because I can't blend two sounds together on pencil and paper and make it sound like something, right? But for the most part, algorithms are, you can think about these independently of the implementation, right? As long as you make certain assumptions in your algorithmic level about what types of data you can represent, you can say I can have lists of numbers or whatever. That it doesn't really matter when you're planning your algorithm what the implementation will be, right? So really a good way, if you're sort of planning a new project, a good way to go is start at the computational level, say, well, what do I want this thing to do, and what information do I have to start with? Then say, all right, what are the steps that I can take to move from input to output? And then lastly, it's like creating an outline for a paper. Lastly, you say, all right, well, now I know the basic steps. Now how do I implement this in code or in pencil and paper or so forth, right? So, what we're really asking you in like problem sets is, if I ask you to write code for something, I'm sort of asking you to come up with both the algorithm and the implementation, but sometimes I kind of give you the algorithm and expect you to just do the implementation step. And like you've seen, sometimes what I've really been wanting you to do is talk to me about algorithms without talking about implementation at all, right? Now I emphasize this because, again, there's some stuff like this on the problem set where sometimes I want you to do an implementation, sometimes I want you to just talk about algorithms. And again, on the exam, I'm not going to ask you anything at the implementation level, right? So like your problem sets and your projects are really where you get to show how you do at the implementation level. On the exam, I'm going to ask you now I'll ask you some questions about how the Python and Matlab languages work that are more conceptual. But if I ask you to do a programming problem, I'm going to ask you to do it at the algorithmic level because I can't expect you to have like the CyclePy and Psychtoolbox like libraries and reference pages memorized. So basically what I want you to do is, by introducing this concept, is I want you guys to start thinking about these levels as separate, right? So if I ask you a question that's targeted at the algorithmic level, I want you to kind of think about the steps independent of how you might do it in code. And this is maybe a bit weird to you, depending on how your process works, but I think it's really helpful because once you get good at this step, it becomes a lot easier to figure out the implementation because you're not doing this sort of trial and error thing where you mix up, where you just sort of like type code randomly in and hope it works. Hopefully hopefully this makes it a little bit easier to have a plan and then go with an implementation. So just to give you a quick example, one sort of problem that beginning computer scientists love to talk about is sorting a list of numbers from like smallest to biggest. And this is because there are a million different ways you can do it, some very slow and some very fast. So at the computational level, you might say, all right, here's our problem that we're trying to solve. We have a one-dimensional list of n items, some number of items of numeric data. We assume that the items in the list are originally not sorted in any particular order. We don't know anything about what order they're in, but probably most of the time they won't be in order. And basically what we want to end up with is a similar type of list with all the same items in it, but now with them all sorted from lowest to highest, right? So computational level, just specifying the problem, right? And it's a pretty simple problem. You could do it in pencil and paper. You could do it lots of ways, right? Now, probably the way you do it with pencil and paper naturally for a small number of items is just look at them all and find the smallest one and write that down, and then find the next smallest one and write that down. And that's a perfectly good sorting algorithm. Actually, I forget what the name of that one is. Now, if you're on a computer, there are all kinds of things you could do. One of the very dumb ones is what's called BOGO sort, whereas you just randomize the list and check to see if it's sorted. And then if not, you just randomize it again and check to see if that's sorted. That's a very slow algorithm for doing this. But let's talk about a more reasonable, not the best algorithm, but a reasonable algorithm for sorting the list, which would be one called the bubble sort algorithm, okay? So this is one that's pretty good and is pretty easy to explain in words. So it's good for talking about at the algorithmic level. So if you're saying, all right, I have a list I want to sort. I don't know yet whether I'm using a computer or my fingers or pencil and paper or what. I don't know what programming language I might use, but let me just think about ways of sorting a list. You could use, one way that might occur to you is to use bubble sort, which basically you would describe like this. Start at the top of the list, look at the first two items. If they are not in order yet, so if the biggest one is first, just switch those two around, right? So make it, instead of the first item followed by the second item, put the second item first and the first item second, right? So now those two items are sorted, right? Now if they are already in order, don't do anything, just leave them sorted. All right, so once you've done that, do that for every pair of items in the list, right? So you sort items 1 and 2, you sort items 2 and 3, you sort items 3 and 4. Now, when you get to the end of the list will not necessarily be sorted because it will be more sorted than it was before, but just individually sorting each pair of items is not enough. Because let's say the smallest item in the entire list was at the very bottom, right? So when you get to the bottom of the list and you switch the last and next to last items, you've moved the smallest item one further up, but you haven't moved it all the way to the top of the list, right? So what you have to do is repeat this process until the list is sorted, right? So go back to the top of the list and say, all right, are the first and second items in order? Okay. Are the second and third in order? If not, switch those. Go to the third and fourth, fourth and fifth, fifth and sixth, etc. Right? And you do that over and over again. And once you get to a list that has no switches necessary, that's totally sorted, you're done. Right? And it's called bubble sort because if you imagine the case where the smallest item is at the bottom of the list, what happens is it kind of bubbles to the top gradually, right? So like, the first time through the list, it becomes the next to last item. Then the next time through the list, it becomes the third to last item, and so forth. Does that algorithm kind of make sense to people? You can kind of see how you would do it on pencil and paper. So the important thing is not that you know how to do this bubble sort thing, but that you understand that this is the level at which I might want you to answer an exam question. If I said, what's a way you might sort a list? If assuming you were the first person to ever come up with bubble sort by yourself, you could describe this. This would be a perfectly good answer describing an algorithm for sorting a list, right? No reference to computers, no reference to Python or Matlab, nothing like that. Just sort of steps, right? Just sort of cognitive steps. And then, of course, the last thing would be the implementation level. So just to show you what it would look like, we don't really care about stepping through it. But if you were typing away in Matlab, this is what you would get if you wanted to implement a simple bubble sort algorithm. So it's not too many lines of code, as you can see. I wrote this morning in about 5 minutes, but I did check that it works. I I mean, I've done this a few times before, so if that seems, maybe it was more like 10, but it was pretty easy. Basically what it does is takes in some list, returns a sorted version of the list, and basically what it does is, oh wait, something's not right there. My little not symbol got taken out somehow. There should be a not symbol there. Because while the list is not sorted, basically you want to go through, check each pair of items. If item I is greater than item I plus 1, meaning that 2 items are out of order, you say the list is not sorted. You switch those 2 items, and you go through and through and through. And basically, the first time you go through the list and everything is sorted, you're done, and you display your sorted lists, right? So it's not super important to step through the code and see exactly how this works, because we've got more important things to do. But the point is, this is an implementation in Matlab, right? But it is actually totally independent of the algorithmic level where we describe the problem, right? The code is just putting this algorithm into the Matlab language, right? Another way to think about this is, think of computer programs as stories, right? Like, if you want to tell the story of Harry Potter, that's like the algorithmic level, right? So the story is the idea that there's a wizard boy and he goes to wizard school in England and there's a bad guy and so on and so forth. Then there's lots of ways you can put that story into words in different languages or using different words to describe a situation. That's all implementation. But the story of Harry Potter is basically the same regardless of the implementation, right? So similarly, the algorithm of bubble sort would be the same whether you did it in Python or Matlab or by hand. And I just want you guys to think about the separation between these things, because I think probably we haven't done a good enough job of separating those all out, okay? So anyway, I just wanted to point this out because I use these terms a bit more in the problem set, computational, algorithmic, and implementation levels. So when I say that I want you to answer something at the algorithmic level, maybe that gives you a better idea of what I mean by that. Okay, any questions about that? Okay, so that's just to clarify basically. I hope that clarifies a bit. And even if you're still not used to kind of thinking about that separation, I think it's a good thing to have in your mind. Okay, so let's go back to the code and step through it a bit more with the time that we've got left today. I had hoped to actually extend this a bit, but I think it's more important that we maybe step through and kind of really think about this algorithm and how it works. One of your problems on the problem set is going to deal with doing a similar sort of thing, basically adding noise to an image. So I had hoped to get to the demo here where we add audio noise to our audio signals, but I don't think we did that yet, if I remember correctly. So we'll see if we can get to that today, but I doubt we will. So we'll probably start with that next week. All that is to say, if you have trouble translating the sound stuff from this demo into like the visual realm, we'll definitely get into that more next Tuesday. And you'll still have until next Friday to finish the problem set. So you may find it easier to start work on problem 2 of the problem set, actually, which is just playing sounds using Psychport audio. It just depends. I mean, at any rate, as you're working on the problem set, I won't belabor the point because we should get to this. But there will be more coming next week that will help you with the problem set if you get stuck. But I think it's still worth playing around with it because in theory you should know everything you really need to know. You just might have to do some creative thinking, which maybe next week will be spelled out for you a bit more. Okay, so anyway, I'm going to start up the demo again. What I'm going to do is basically get us back to the point where we were before we stopped, which is right here after we equalized the sound wavelengths. So I'm going to skip through the stuff that is pretty straightforward. So we said last week initialize psych sound is just something you have to do to prepare your computer to play sound. Apparently you only have to do it on Windows, but it doesn't hurt to do it on the Mac as well. And we're going to use this command, which is the Psychport audio open command, right? And what that does is that opens basically a device to play sound, right? And again, you don't have to worry about the details, really. Basically, the idea is that my sound, you can see it's just the number 3. What this just means is there's now some object in your system that is prepared to play sound. Just like you have like these window objects, right? This is a sound object. So when you draw into a window, we need to give a window, which we'll be doing shortly. Oh shoot, I forgot that we can't step through this stuff, right? So maybe we'll just talk through it a bit. When you create a window, you have a window object that you refer to and that you draw all the stuff into. When you have a sound object, you have a sound object that you fill with sound and then tell it to play itself, basically, right? So maybe let's talk through this code a bit and then run it, and then we can talk through it again, because I forgot once we open up the window, we won't be able to see the code. So what we're going to do, right, is we're going to initialize Psychtoolbox, which will give us a window object and a rectangle, which again is just saying a rectangle in Psychtoolbox is just 4 coordinates, right, which represent the left, top, right, and bottom boundaries of the screen. And under most conditions, if I have a 1024 by 768 screen, that rectangle is going to be the numbers 0, 0, 1024, and 768, representing the pixel numbers of the left, top, right, and bottom boundaries. So once we step through that, we can then calculate the center in American English spelling, because we're writing code, which is usually American English. We can calculate the center pixels, which we might need, by just taking the first element of the rectangle and the third element of the rectangle, adding them together and dividing by 2, which means we average them, right? So if the left boundary of your screen is 0 and your right boundary is 1024, then your center pixel in X will be 512. Do the same thing with Y. So if the top of your rectangle is 0 and the bottom is 768, average them together, and your Y pixel is going to be, what is that? 384, I think. All right, so we're going to calculate the center pixels, which we might need. Then we're going to want to display our instructions text. And I think this stuff should not be too difficult for you guys, right? So, because we do a for loop through the instructions text, or through the length of the instructions text, right? So we said the instructions text has 3 items in the cell. So we're going to go through this for loop 3 times. The first thing we're going to do is just flip our window, which clears it out. We use wait sex, which just does nothing for half a second. It's just like the wait command in PsychoPy. It just is sort of something to space out your timing. Then we're going to use this draw formatted text, which is a command for drawing text in PsychoPy, right? And what you give it is your window, the text that you want to draw, and hopefully by now the cell stuff makes more sense, right? So we tell it, we want to give it instructions text, curly bracket I, which is going to be the first of those long strings of instructions, that 125 character string, which is please place the index, middle, and ring fingers of your right hand on the 1, 2, 3 keys, etc. Right, so we tell it what text we want it to draw. You tell it the X and Y coordinates you want to draw to, and if you want them to just be centered, you can just say center. And we're going to give it the text color, which you remember we defined up above as being white, right? Full numbers on all of the red, green, and blue channels. Okay, so draw formatted text can take all of those parameters, and that will draw the text to the off-screen window. Then, of course, we have to flip the window so that the text actually appears on the screen. And then we're going to wait for a key press, right? And KB wait, like we said before, you can use that to get the actual key press. And again, remember that we said these empty brackets in this 2 are just kind of specifying modes of KB wait. This is basically the best way to specify the modes for our purposes, but if you just called KB wait like that, that would be fine too, because these are pretty close to the default modes anyway. So that's just going to wait for a key press, and in this case we don't care what key is pressed, right, because we tell them to press any key. So we don't need to save what key is pressed. We can just tell it to wait for a key and then go on, right? Does that part make sense to everybody so far? So maybe let's do this. So let's stop the code again after that part. Just okay, so we initialize Psychtoolbox. We've drawn the text, right? So this is the first item in our text cell, our instructions text cell, drawn onto the screen in the center. Press any key to continue. Here's the second one. Notice that half-second pause, right, of nothing in between each one. Press any key to begin the task. Okay. So now we're stuck back in our debugger again, but of course the screen is here. So what I'm going to do is, oops, I thought that was going to work. Okay. So now what I've had to do is I've had to clear away my Psychtoolbox window. So the next time I try to draw something on the window, it's going to crash. But we can step through a few lines of code before it does that, so we can kind of see how things are going to go from there on. Okay, so we're stuck here now after we've drawn stuff. I think, let's see, are we still in the debugger? Okay, yeah. So we've computed our X and Y center, you see. We've got this window rect, which as I predicted is 0, 0, 10, 24, 68. We've got a window, which is window number 10, whatever that means. Okay, so what we're going to do here, before we start the trials, we're going to want to have a list of, like when we get done running the task, we're going to want a list of what sounds we played, what text we showed, right? What syllable text we showed, and what responses were and what the RTs were, right? So that we can save our behavioral data at the end. And we're probably not going to get into writing out files in Matlab, but you know, what we do have at the bottom is just a text display to the Matlab window of what all of our data was from all of our trials, right? So hopefully now that we've stepped through this before, it should be pretty obvious what we're doing, which is just creating empty lists, one for the sound 1, one for sound 2, in each pair of sounds that are blended together, one for the text that was shown, one for the response we collected, and one for the RT. Those are empty lists now, or empty Matlab matrices. And of course what we're going to do is add to those on each trial, right? So just like we did before, in an earlier loop, we're going to create an empty list and then add to them each time we go through a trial. So let's see if we can get through the for loop through the trials before we end. And then we'll kind of pick up next time with modifying this text and thinking about some other topics. So we want to loop through trials, right? So we said that we're going to have 10 trials. So this for loop is going to run 10 times. So I is going to start off at 1, trial 1. The first thing we're going to want to do is pick 2 of the 3 sounds to blend together and use on this trial, right? So I think I asked you previously in one of the problem sets about the randperm function, right? And what the randperm function does, like if I say randperm 5, it gives us the numbers from 1 to 5 in random order, which is a pretty useful thing a lot of the time. Because basically, oops, close this. Oh no! Let's see if I can, no, if I can't get out of that. I should not have done that. There's a little bug in this version of Matlab where sometimes if you close a window, it crashes. And apparently it crashed that time. Basically what we're going to do though, so if we want to blend 2 sounds together, we have sounds 1, 2, and 3, right? Ba, da, and ga, that we are going to want to blend together 2 of those. And of course we don't want to blend together sound 1 with sound 1, or like you don't want to blend ba with ba, because that's just ba. So we want to make sure we select 2 unique sounds, right? So one way of doing that pretty easily in code is to make a list of numbers 1, 2, and 3 in random order and take the first 2 of those numbers, right? That's not the only way you could do it, but it's one easy way to do it. All right, so see if I can magically get out of here. Well, I might have crashed things pretty good here. Let's try this one more time. Okay, now I'm crashing all over the place. Well, this might be it for today. Let's see if I can get to this point. Let me actually pull another little trick here. Let's just do this instead. Sorry, I do want to get to the end of this for loop at least quickly, but I think hopefully this will make more sense now that we step through the early stuff. All right, so let's do this real quick. Just add in a close all the screen stuff. So SCA, remember, is back in the dark days before we figured out our trick for magic cleanup, which apparently doesn't always work. That closes any screens So we'll just kind of step through after the text and then close the window. Okay, so closes the screen. Now we're back here. Okay, so if we, oh shoot. Okay. So now we're back in the debugger. All right, so if we get a random permutation of the numbers 1, 2, and 3, like 3, 1, 2, then we can make sure that if we pick the first and second items in that randomly sorted list, we get two numbers between 1, 2, and 3 that are different, right? So 3 and 1, right, because the list was 3, 1, 2. So now we've said that we're going to take syllable 3 and syllable 2, and those will be our first and second sounds that we blend together. So in other words, we're going to take ga and blend it together with ba. Now this is a line that's pretty complicated, so this is maybe the hardest one to think about. So maybe we'll just explain this one and then take off. So what we're doing here, and this is, pay close attention because this is, you'll want to do a similar thing in your homework for picture data instead of sound data. We're basically just blending these two sounds together. So what we're doing, right, remember we had all of our sound data in the sound cells variable, right? And we went and did all the necessary stuff. We made all the sounds the same length, right? They're all 9,675 samples long. So what we really want to do is take two of these matrices and blend the values in them together, right? Now, if we wanted to just average them, that would be easy to do because we could just add the two matrices together. And remember, if you add two matrices, as long as they're the same length, just every element in the sum matrix is the corresponding elements from the original two added together, right? So I could just say, like if I just wanted to add together my first sound I could do that. And really, if I wanted to average them, I could do that and divide by 2. But that would only give me an exact 50% blend of those two sounds, right? So in other words, here I'll plot it on screen. If I wanted to plot like ba, that's sound cells 1, right? So there's ba in blue, and then plot da in red, right? So there's ba and da on top of each other. Now if I wanted to plot in green the average of ba and da, I could just plot sound, sound cells 1 plus sound cells 2 divided by 2 in green. So in other words, that just takes every item in each sound wave, it's a little hard to see, and averages them, right? If you add two matrices together, you get the sum, and then of course you can just divide everything in that list by 2, and you get the average of those two matrices. It's a little hard to see, but you can take my word for it. But the tricky thing we want to do here is we don't just want to average these two things together, we want to blend them in some predefined proportion, right? So what we really want to do is take 52% of the first sound and whatever 1 minus 52% is, so 48% of the second sound, and add those together, right? So we have a little bit more of the first sound in the mix than the second sound, right? And we do that by saying, all right, well the sound proportion is 52%, or 0.52 really. So if you take the first sound that we want to blend together and multiply that by 0.52, that basically gives us a quieter version of the first sound. That's 52% as loud as it was originally. And then we take 1 minus sound proportion, so that's going to be 48%, right, 0.48. And multiply that by the second sound. That's going to give us the second sound, but 48% as loud as it originally was. And add those together, that's going to give us an output sound that is the same sort of overall volume as the original two sounds were, but it's a blending of them together with 52% being the first sound and 48% being the second sound. Does that kind of make sense to people? All right, so just very quickly, then we're going to randomly select which syllable, the number of the syllable to display. So we're going to display the third syllable using this random eye function, right? So we're going to display ga on screen and just get that text to display out of the syllables list. So this text is going to be ga. Then all we have to do is use Psychtoolbox functions to fill up our buffer, which means to put the sound data into the sound device, right? So we say fill my sound device with the sound that we've created, and I'm not going to do that because I cleared out the sound buffer, I think, and it's now, well, we can try it. Oh no, it's okay, it's okay. I'm not going to call this because it'll crash because I've already cleared out that window. But basically, we fill up our sound device with the sound data that we just made. We draw some text on the screen, which you guys should be able to figure out now that we've kind of stepped through that. We start the sound playing, and then essentially we wait a little while, draw our text for what responses are what on the screen, and then we wait for a key press. And I know we haven't really stepped through this key press waiting loop yet, but you won't have to do this in the problem set, so it's not too critical that we do it this time. But basically it's very similar. If you look at this, it's very similar in structure to what we did when we were checking for key presses in PsychoPy. So you can, if you take a look at it, you can probably pretty much figure it out. But we can talk about that more next time. Okay, so we didn't quite get to the end of this, but I think we can wrap this up and then kind of extend it a bit next time and talk about some plotting and stuff, which we've already very briefly. Well, here's your first lesson in Matlab plotting, is you can do stuff like this. But we'll get more into that later. So hopefully that'll give you enough to start on the problem set. Really, I think, if you come and ask me a question or two, you've probably got enough to do the whole problem set. Hopefully that makes the stuff we did before make a little bit more sense. So, feel free to take some time making sure you understand this code. I think that'll help you with the problem set. But of course, like I said, in the problem set, again, you'll have to do this with picture data. So you do a similar sort of thing with picture data, where you add noise to a picture. So we can talk about that more one-on-one if you have questions about that. But that will all make more sense after next week. Okay, any questions before we wrap up? All right, so sorry, due to those technical issues, we didn't actually end early. We actually ended a bit late, but we're done. So yay.